Welcome to Section 2 of the CSWIP 3.1 Welding Inspector Training Program, Terms and Definitions. Before we can inspect a weld properly, we need to establish a common technical language. A welding inspector must be able to look at a joint, identify its configuration, describe its preparation, identify the features of the completed weld, and communicate those observations using the correct terminology. This section is therefore much more important than it may initially appear. These are not simply vocabulary words to memorize. They are the terms that you will use when reading drawings, reviewing welding procedures, inspecting fit-up, evaluating completed welds, communicating with welders and engineers, and answering examination questions. We will begin with the fundamental definitions of welding, weld, joint, brazing, and braze welding. Then we will move into the 6 basic joint configurations: butt, T, corner, edge, cruciform, and lap joints. From there, we will distinguish between different weld configurations, including butt welds, fillet welds, slot welds, and plug welds. We will then examine full and partial penetration joint classifications and the terminology used to identify the different regions of a completed weld. After that, we move into weld preparation geometry. This includes bevel angle, included angle, root face, root gap, root radius, and land, followed by the different single-sided and double-sided preparations. The second half of the section becomes particularly important for examination purposes. We will cover butt weld sizing, fillet weld geometry, throat thickness, leg length, and the important relationship. A equals 0.707 multiplied by Z. Finally, we will cover ISO 6947 welding positions and the practical differences between weaving and stringer bead techniques. Throughout this section, keep one principle in mind. Do not learn these terms only as definitions. Learn to recognize them in an actual weld. That is the skill expected from a competent welding inspector.
This slide establishes what you should be able to do by the end of this section. The first requirement is to understand the fundamental definitions from BS 499-1. You should be able to distinguish welding from brazing and braze welding, and understand exactly what is meant by a weld and a joint. Next, you need to recognize the 6 joint configurations and understand the angular ranges associated with each one. You also need to distinguish between weld configurations. A butt weld is not the same thing as a butt joint, and a fillet weld is not limited to one particular joint type. We will also examine full penetration and partial penetration welds and then move into joint classification, including homogeneous, heterogeneous, and dissimilar or transition joints. Another major objective is the identification of completed weld features. You should be able to locate the parent metal, weld metal, heat-affected zone, fusion line, weld face, root, toe, and excess weld metal on a cross-section. The preparation terminology is equally important. You should understand bevel angle, included angle, root face, root gap, root radius, and land, and recognize square, V, U, bevel, and J preparations. Fillet weld sizing is one of the areas where theory becomes calculation. You must be comfortable moving between leg length and design throat using the appropriate relationship. Finally, you need to recognize the ISO 6947 welding positions and understand the practical difference between weaving and stringer bead deposition. For examination preparation, do not simply memorize the list. Test yourself by looking at an unfamiliar weld sketch and asking, what joint is this? What preparation is being used? What weld configuration is present? Where is the root? Where is the toe? What dimensions would I inspect? That is how these definitions become inspection knowledge.
Let us start with the basic terminology. According to the presentation, the BS 499-1 definition of welding describes an operation in which 2 or more parts are united using heat, pressure, or a combination of heat and pressure, producing continuity in the nature of the metal between the parts. The phrase continuity in the nature of the metal is particularly important. Think about the difference between welding and mechanical joining. A bolted connection joins two components mechanically, but the metals themselves do not become continuous across the joint. Welding creates a metallurgical connection. A weld is the resulting union of pieces of metal produced by welding. A joint, on the other hand, describes the connection where components have been prepared and assembled for joining by welding or brazing. Now compare these concepts with brazing. In brazing, the filler metal melts above 450 degrees Celsius, but remains below the melting temperature of the parent material. Capillary attraction draws the molten filler into the joint. This is a key distinction. In braze welding, the filler metal again has a lower melting temperature than the parent material, but the process does not rely on capillary action, and the parent metal is not intentionally melted in the manner of fusion welding. This is also where candidates frequently confuse brazing with soldering. The temperature criterion is important. Brazing uses a filler melting above 450 degrees Celsius, whereas soldering uses a filler melting below 450 degrees Celsius. From an inspection perspective, never assume that a joint containing filler metal has been fusion welded. The joining process must be correctly identified because the terminology, procedure requirements, and acceptance criteria can be different. A useful examination strategy is to focus on the defining feature of each process rather than memorizing long sentences. For brazing, remember capillary attraction. For braze welding, remember no capillary action and no intentional melting of the parent metal. For welding, remember continuity in the nature of the metal. With those fundamentals established, we can now look at how welded joints themselves are classified.
This slide introduces the structure of the next part of the section. There are 6 fundamental joint configurations that you need to recognize: butt, T, corner, edge, cruciform and lap. Notice that the classification is based primarily on the relationship between the components being joined. This is different from classifying the weld itself. For example, a T-joint may contain a fillet weld, but it may also contain a butt weld if the design requires complete penetration through the T configuration. That distinction is extremely important for both inspection and examination questions. The section will also introduce slot and plug welds, autogenous welds, and the difference between full and partial penetration. Finally, we will look at whether a joint is homogeneous, heterogeneous, or dissimilar. As an inspector, this terminology helps you describe what you actually see rather than making vague statements such as, "This is a T-weld." A technically stronger description might be, "This is a T-joint containing a fillet weld," or "This is a T configuration with a complete penetration butt weld." That level of precision is what we are aiming for. This is one of the slides where memorization and visual recognition need to work together. The first joint is the butt joint. The two components are aligned end-to-end or edge-to-edge, with an included configuration angle from 135 to 180 degrees. Next is the T-joint. One component meets the face of another, with the joint configuration ranging from greater than 5 degrees up to and including 90 degrees. The corner joint occupies the range greater than 30 degrees but less than 135 degrees, where the ends or edges of two components meet. The edge joint is associated with the smaller range from 0 through 30 degrees. A cruciform joint is formed at right angles. The components intersect to produce a cross-shaped arrangement. Finally, the lap joint involves overlapping components, with the relevant configuration falling within the 0 to 5 degree range. For examination purposes, the angle ranges are worth learning accurately. But do not rely on the numbers alone. Associate each range with a physical picture. Butt means almost in line. T means one member approaches the face of another. Corner represents an angled meeting of edges. Edge involves closely aligned edges. Cruciform creates a cross. Lap involves overlapping members. One common source of confusion is the difference between a T-joint and a corner joint. In a T-joint, the end or edge of one component meets the face of another. In a corner joint, the ends or edges of the two components meet at an angle. When you are studying these classifications, always look at the geometry first and the terminology second. The visual relationship between the components is what allows you to identify the joint correctly. Now we move from joint configuration to weld configuration. A butt weld is a weld made in the plane of the joint. It is commonly associated with butt joints, but it can also occur in T and corner configurations when the design requires that type of weld. A fillet weld has an approximately triangular transverse cross-section. It is commonly associated with T, lap and corner joints. This is an important distinction. A T-joint does not automatically mean a fillet weld. Next, consider the autogenous weld. An autogenous weld is a fusion weld made without adding filler metal. The material that forms the weld comes from the parent materials themselves. This can occur in processes such as TIG, plasma, electron beam, laser, or oxy-fuel welding when no filler is introduced. Now compare slot and plug welds. A slot weld uses a hole or slot in one overlapping component, with a weld made around the periphery of the opening to connect that component to the material beneath it. A plug weld, in contrast, uses a circular or oval hole that is filled with weld metal to join the overlapping components. This is an excellent example of why visual recognition is important. When looking at an overlapping connection, ask yourself, is the weld around the opening, or is the opening filled with weld metal? That distinction helps separate slot welds from plug welds. From an inspection standpoint, the configuration also affects where you look for defects and how you determine the relevant dimensions. Now we need to distinguish between full penetration and partial penetration. A full penetration weld extends completely through the joint thickness and achieves complete root fusion. In American terminology, you may encounter the terms complete joint penetration, or CJP. A partial penetration weld does not extend completely through the joint thickness. The corresponding American terminology is partial joint penetration, or PJP. The important point for an inspector is that partial penetration is not automatically an unacceptable condition. Whether it is acceptable depends on the design requirements, specification, drawing and applicable welding procedure. The required penetration must be established before the inspection is performed. Now we introduce another classification: homogeneous, heterogeneous and dissimilar or transition joints. A homogeneous joint is one where the weld metal and parent material do not have significant differences in composition or mechanical properties. A heterogeneous joint has significant differences between the weld metal and parent material. A dissimilar or transition joint involves significant differences between the two parent materials. This distinction becomes particularly important when considering welding procedure qualification, metallurgy, and the effects of the welding thermal cycle. For example, welding carbon steel to an austenitic stainless steel is not simply another carbon steel welding operation. The materials respond differently to heat, have different metallurgical characteristics, and may require special procedure controls. As an inspector, your job is not to redesign the joint. Your job is to understand what the design and qualified procedure require, and then verify that the work complies with those requirements. This diagram is extremely important because it establishes the terminology used to describe a completed weld. Start with the parent metal. This is the original material being joined. It remains outside the melted weld region. Next is the weld metal. This is the metal that has melted during welding and remains in the completed weld. Adjacent to the weld metal is the heat-affected zone, or HAZ. The HAZ is particularly important because the material in this region has experienced sufficient heat to alter its metallurgical condition, but it has not itself melted. That means the HAZ can have different hardness, toughness, microstructure, and cracking susceptibility compared with the unaffected parent material. The fusion line forms the boundary between the weld metal and the HAZ. The combined region containing weld metal and HAZ is referred to as the weld zone. Now look at the external geometry. The weld face is the exposed surface on the side from which the weld was made. The toe is the boundary between the weld face and parent metal. The root is associated with the deepest part of the weld and the side of the joint furthest from the welder during the relevant operation. Finally, we have excess weld metal, which extends beyond the plane connecting the toes. These terms are not simply labels on a diagram. During visual inspection, each one represents a specific location where geometry, discontinuities, or defects may need to be evaluated. In particular, pay close attention to the toe because abrupt changes in geometry can create stress concentration. Once you can confidently identify these features on a butt weld, you can transfer the same reasoning to other weld configurations. The fillet weld has many of the same fundamental features, but its geometry is different. The cross-section is approximately triangular, and the two members form the fusion faces. The toe is again an important inspection location because it represents a transition between the weld and parent metal. A poor toe profile can create a sharp geometric discontinuity and increase local stress concentration. The root is located at the junction of the two members at the deepest part of the fillet configuration. Whether fusion exists at this location depends on the actual weld design and process requirements. The HAZ develops in both parent metal members because both components are exposed to the welding thermal cycle. The weld face is the visible external surface of the fillet weld. When examining the cross-section, remember that excess weld metal can extend beyond the ideal geometric profile. For a conventional miter fillet, the idealized cross-section is an isosceles right triangle. That geometry is the basis of the familiar throat-to-leg relationship that we will calculate later. From an inspection perspective, do not judge a fillet weld only by whether it looks large. A large weld is not necessarily a good weld. The inspector must consider the specified weld size, profile, fusion, penetration, toe condition and applicable acceptance criteria. That is why correct terminology and measurement are essential. This slide brings together the terminology we have just seen. Let's make the distinctions very clear. Parent metal is the material being joined or surfaced. Filler metal is metal deliberately added during welding, braze welding, brazing, or surfacing. Weld metal is the metal melted during formation of the weld and retained within the weld. This gives us an important examination distinction. Filler metal describes what was added. Weld metal describes what ultimately melted and remained in the weld. The weld metal may therefore contain material originating from the filler and, depending on the process and joint, melted parent material. The HAZ is parent material affected metallurgically by welding or thermal cutting but not melted. The fusion line is the boundary between weld metal and HAZ in a fusion weld. The weld zone contains both the weld metal and HAZ. The weld face is the exposed surface on the side from which the weld was made. The root identifies the region on the side of the first run furthest from the welder. And the toe is the boundary between the weld face and parent metal. Finally, excess weld metal is material extending outside the plane connecting the toes. There are several common examination traps here. Do not confuse HAZ with weld metal. HAZ is heated but not melted. Do not confuse weld zone with weld metal. Weld zone includes both. And do not treat filler metal and weld metal as identical terms. As an inspector, precise terminology improves the quality of your inspection reports because another engineer should be able to understand exactly which region you are describing. We now move from the completed weld back to the joint preparation. Joint preparation is one of the most important stages before welding begins. The geometry established before welding directly influences access, penetration, filler metal volume, heat input, distortion, and the ability of the welder to achieve the required weld quality. The principal preparation features include the angle of bevel, the included angle, the root face, the root gap, the root radius, and the land. We will also examine open square preparations, V preparations, U preparations, bevel preparations, and J preparations, including both single-sided and double-sided configurations. Backing arrangements will also be considered. The governing preparation recommendations referenced in this section include BSEN ISO 9692. From an inspector's point of view, preparation inspection is a fit-up inspection activity. Before welding begins, you may need to verify dimensions, alignment, cleanliness, root condition, preparation angle, and backing arrangements. This is important because once welding has started, correcting an incorrect preparation becomes more difficult and expensive. A good welding inspector therefore does not wait until the weld is complete. Inspection starts with the joint preparation. Double-sided preparations become particularly attractive for thicker materials when both sides of the component are accessible. The major advantage is reduced weld volume. A double V preparation generally requires less filler metal than an equivalent single V preparation. That means less welding time, lower material consumption, and potentially lower distortion. There is also an important thermal advantage. Welding from both sides can help balance the thermal effects and reduce angular distortion. The presentation also introduces the asymmetric double V preparation. In an asymmetric arrangement, more weld metal may be deposited from one side and the remaining portion completed from the opposite side after appropriate preparation of the root. This approach can be used to balance the welding sequence and reduce distortion. The W preparation provides an even greater reduction in weld volume and can therefore be particularly advantageous for very thick sections. However, the manufacturing cost is higher because machining is generally required. Double bevel and double J preparations are especially useful in T-joint applications because only one component may require preparation. The important practical limitation is straightforward. Double-sided preparations require access to both sides. In real fabrication, preparation selection is therefore a compromise between weld volume, preparation cost, access, distortion control, production time, and the required weld quality. The inspector should understand why a particular preparation was selected because it helps explain what dimensions and conditions need to be controlled during fit-up. We now move into weld sizing. This section is particularly important because it connects weld geometry with measurable quantities. For butt welds, we need to distinguish between design throat and actual throat. For a full penetration butt weld, the design throat is associated with the required joint thickness. If excess weld metal remains above the parent surface, the actual throat can be greater than the design throat. If the weld face is ground flush, that excess has been removed and the actual throat corresponds to the design requirement. When joining plates of different thicknesses, the design requirement is related to the thinner component, while the actual geometry of the completed weld may extend through the joint thickness. We also need to understand run and layer. A run is the metal deposited or melted during one pass of the electrode or torch. A layer is a stratum of weld metal that can consist of one or more runs. This distinction becomes important when discussing multi-run welding and procedure qualification. Finally, a single-sided weld is made from one side of the joint, with the root region on the opposite side. As you inspect welds, remember that dimensions should not be judged only visually. If a drawing specifies a weld size, the inspector needs an appropriate measurement method and the applicable acceptance requirements. The next slide will take this principle further with fillet weld geometry, where a simple mathematical relationship becomes one of the most important calculations in this section. A fillet weld is a fusion weld with an approximately triangular transverse cross-section. For inspection purposes, three dimensions are particularly important. The first is the actual throat thickness. This represents the perpendicular distance associated with the actual weld geometry between the relevant surfaces. The second is the design throat, often identified by the symbol A. This is the minimum effective throat required by the design. The third is the leg length, identified by Z. The leg length is measured from the intersection of the fusion faces to the toe along the relevant fusion face. For a conventional equal-legged miter fillet weld, these dimensions are related by a simple geometric relationship. A equals 0.707 multiplied by Z. In the opposite direction, Z equals 1.41 multiplied by A. The reason for the factor 0.707 comes directly from the geometry of an isosceles right triangle. The perpendicular throat is the altitude associated with the 45-degree geometry, and the sine of 45 degrees is approximately 0.707. For example, if the leg length is 10 mm, the theoretical design throat is approximately 7.07 mm. If the required throat is 10 mm, the corresponding equal leg length is approximately 14.1 mm. But there is an important limitation. This simple relationship applies to the conventional equal-legged geometry within the specified fusion face angle range. It should not automatically be applied to asymmetric or otherwise non-standard fillet profiles. That distinction is essential for both examination calculations and field inspection. The shape of a fillet weld is not merely an aesthetic issue. It affects stress concentration, effective throat, inspection, and fatigue performance. The miter fillet has approximately equal leg lengths and a relatively flat face. This is the geometry from which the familiar 0.707 relationship is derived. A convex fillet has a weld face that bulges outward. Excess weld metal may increase the actual throat, but excessive convexity can create an unfavorable toe transition and increase local stress concentration. A concave fillet curves inward toward the joint. Its smooth transition can reduce stress concentration at the toe, which can be beneficial in fatigue-sensitive applications. An asymmetric fillet has unequal leg lengths. Because the geometry is no longer an isosceles right triangle, the simple 0.707 relationship cannot automatically be used. The final configuration is the deep penetration fillet weld. Here, increased penetration contributes to the effective throat without requiring the same amount of deposited surface weld metal. The presentation identifies the throat using the symbol S for this configuration. Deep penetration fillets can be produced using suitable high-productivity welding processes and controlled parameters. However, deeper penetration and a high depth-to-width ratio can introduce metallurgical risks, including increased susceptibility to centerline solidification cracking under certain conditions. The inspector therefore needs to understand not just the weld size, but the relationship between weld profile, penetration, and the qualified welding procedure. Now let's apply the basic relationship to actual calculations. Remember the two equations. A equals 0.707 times Z. And Z equals 1.41 times A. Suppose the measured or specified leg length is 10 mm. Multiplying 10 by 0.707 gives approximately 7.07 mm. So the corresponding theoretical design throat is approximately 7 mm. Now consider a 14 mm leg. 14 multiplied by 0.707 gives approximately 9.9 mm, which we can reasonably associate with a 10 mm throat requirement under the applicable geometry. Now work in the opposite direction. If the drawing requires a design throat of 10 mm, multiply 10 by 1.41. The result is approximately 14.1 mm. Therefore, for the conventional equal-legged geometry, an inspector would expect approximately a 14 mm leg length. There is another important part of this slide: correction factors for fusion face angles outside the normal range. This is where careless application of the 0.707 factor can lead to an incorrect answer. The simple factor applies to the appropriate conventional geometry. When the fusion face angle changes, the relationship must be corrected using the applicable factor. For examination purposes, pay close attention to the angle range specified in the question before starting the calculation. For field inspection, never calculate a required weld dimension using a remembered formula without checking the drawing, specification, and applicable design basis. The mathematics is simple. The engineering judgment is knowing when that mathematics is valid. We now move into welding positions according to ISO 6947. These position codes are essential knowledge for a welding inspector. The principal codes shown here are PA, PB, PC, PD, PE, PF, and PG. PA represents the flat position. This is generally the most favorable position because gravity assists control of the weld pool. PB is the horizontal vertical position, commonly associated with fillet welding. PC represents the horizontal position for the relevant butt weld configuration. PF is vertical up welding. The weld progresses upward, and this generally allows good control and penetration when the process and parameters are appropriate. PG is vertical down welding. The welding progresses downward. This can provide higher travel speed and productivity, but penetration behavior differs from vertical up welding. PE is the overhead position. The welder is depositing weld metal above the head, making control of the molten pool particularly demanding. Finally, PD represents the horizontal overhead position. For examination purposes, do not learn these codes as isolated letters. Associate each code with the physical direction and orientation of the weld. As an inspector, welding position is important because it can affect welder qualification, procedure qualification, welding technique, deposition behavior, penetration, and the difficulty of maintaining weld quality. When reviewing a welding procedure or welder qualification record, always check that the position being used is covered by the relevant qualification. The previous slide introduced the position codes. This slide explains an important detail. The actual welding position is not simply a label such as vertical or horizontal. ISO 6947 defines positional ranges using geometric parameters such as slope and rotation. Slope describes the inclination of the weld axis relative to the horizontal reference. Rotation describes the orientation of the weld cross-section. The diagram provides tolerance windows for the various welding positions. Why does this matter to an inspector? Because a welder qualification is not necessarily unlimited. The qualified position must cover the actual position being used. Similarly, a welding procedure specification may identify the permitted welding position or range of positions. If the actual weld falls outside the applicable qualification range, the inspector should not simply assume that the qualification remains valid. This is why position qualification must be checked against the governing qualification standard. A useful practical approach is to think in terms of geometry rather than names. Instead of asking only, "Is this a vertical weld?" determine the actual slope and rotation and compare them with the applicable qualification range. This becomes especially important on complex fabrications where the weld may appear approximately horizontal or vertical but actually fall into another position category. The key message is simple: welding position is a controlled qualification variable, not merely a description of welder posture. The final technical topic in this section is the difference between weaving and stringer bead techniques. A weaving technique involves transverse movement of the electrode or torch during deposition. This allows the welder to cover a wider area with a single pass and can be useful where the groove or joint geometry requires broader coverage. However, excessive weaving can create problems. It can increase heat input per unit length, enlarge the HAZ and potentially contribute to defects such as undercut, overlap, or inadequate sidewall fusion if the technique is poorly controlled. A stringer bead, by comparison, uses little or no transverse oscillation. The bead is relatively narrow, and several stringer beads may be deposited to fill a wider joint. This can provide better control of heat input and distortion and can be advantageous for materials where excessive heat input is undesirable. There is also an important metallurgical consideration. In multi-pass welding, subsequent passes can thermally affect the HAZ created by earlier passes. Under suitable conditions, this can produce a tempering effect and influence hardness and toughness. For hydrogen-sensitive or higher-strength materials, controlling heat input and bead technique can be particularly important. From an inspection perspective, the welding technique should not be judged independently of the qualified welding procedure. The WPS may specify limits on weave width, interpass temperature, heat input, travel speed and other variables. Therefore, if the procedure requires stringer beads, a welder should not simply substitute a broad weaving technique because it appears faster. The correct technique is the one permitted by the qualified procedure and suitable for the material and joint. This slide is designed as a rapid revision tool. The important numbers should now start to become familiar. For the typical single V preparation shown in this presentation, remember the bevel angle range and understand that the included angle is related to the bevel geometry. For AU preparation, remember that the bevel geometry is narrower and generally requires machining. For the representative MMA carbon steel full penetration example, the root face and root gap dimensions shown here are important examination values. The most important mathematical relationship remains A equals 0.707 times Z. And the reverse relationship is Z equals 1.41 times A. The welding position codes must also be immediately recognizable. PA is flat. PB is horizontal vertical. PC is horizontal. PF is vertical up. PG is vertical down. PE is overhead. PD is horizontal overhead. The brazing temperature criterion should also be remembered, above 450 degrees Celsius for brazing, while below 450 degrees Celsius corresponds to soldering. Then there are the joint classifications. Homogeneous means there is no significant difference in properties between the relevant materials. Heterogeneous indicates a significant difference between weld metal and parent material. Dissimilar or transition joints involve significant differences between the parent materials. Finally, remember the practical significance of concave fillet welds and the special geometry of deep penetration fillets. The best way to use this slide is not to read it repeatedly. Cover the answers and attempt to reconstruct them from memory. If you can recall the numbers, definitions and relationships without looking, your understanding is becoming examination ready. This slide brings the entire section together. First, remember the core definition of welding and the phrase continuity in the nature of the metal. Second, understand the distinction between brazing, soldering and braze welding. Third, memorize the 6 joint configurations and their associated angle ranges. Fourth, remember the importance of the toe. It is a geometric transition where stress concentration can become significant, particularly under cyclic loading. Fifth, distinguish full penetration from partial penetration and understand the CJP and PJP terminology. Sixth, know the 3 joint classifications, homogeneous, heterogeneous and dissimilar or transition. Seventh, understand how included angle relates to bevel angle. Eighth, know the representative root face and root gap dimensions given in this course material and, importantly, understand that these are preparation requirements for the specific application described rather than universal values for every welding situation. Ninth, know the fillet-weld relationship. A equals 0.707 times Z. And remember its geometric limitations. 10th, understand the difference between design throat, actual throat and excess weld metal. 11th, recognize the significance of fillet weld profile, including concave and deep penetration configurations. And finally, know all 7 ISO 6947 position codes. At this point, I recommend closing your notes. Try to reproduce these 12 points from memory. Then take a blank sheet of paper and draw a butt weld and a fillet weld. Label the parent metal, weld metal, HAZ, fusion line, toe, root, weld face and excess weld metal. Next, write the fillet weld equation and solve one example in each direction. Finally, write all 7 ISO position codes. If you can perform those tasks without referring to the presentation, you have developed a much stronger foundation than simply memorizing the slide content. We have now completed Section 2, terms and definitions. We began with the fundamental concepts of welding, welds, joints, brazing and braze welding. We then examined all 6 joint configurations and learned how their geometry is classified. We distinguished between butt, fillet, slot, plug and autogenous weld configurations and examined the difference between full and partial penetration. We identified the major regions and features of completed welds, including parent metal, weld metal, HAZ, fusion line, weld zone, root, toe and weld face. We then moved back to the preparation stage and studied bevel angles, included angles, root faces, root gaps, root radii and lands. We compared single-sided and double-sided preparations and considered the practical reasons for selecting different joint geometries. We also examined butt weld sizing and the difference between design and actual throat. Then came one of the most important examination calculations in this section, the relationship between fillet weld throat and leg length. Remember, A equals 0.707 times Z, and Z equals 1.41 times A. But equally important, remember when that relationship is valid. Finally, we covered the ISO 6947 welding positions and the practical differences between weaving and stringer bead techniques. Before progressing, make sure you can perform 3 tasks confidently. First, draw and label a butt weld and a fillet weld. Second, calculate throat from leg length and leg length from throat. Third, identify all 7 ISO 6947 welding positions. If you can do those 3 things accurately, you have a strong foundation for the next stage of the course. In Section 3, we move from terminology into a subject that is central to welding inspection, welding imperfections and materials inspection. There, the terminology we have established becomes practical inspection knowledge. So take a moment to consolidate these definitions, because from this point forward, we will use them continuously.